So then a few words just at the end about volcanic hazard and the mitigation. And here's a postcard from Seattle when I was there a few years ago. I liked that postcard with Mount Rainier looming in the background there. And it gives you a sense of a very vulnerable society close to a big volcano. And I just talked to a gentleman a few minutes ago at the beginning of our little session from Mexico. And there's, of course, places like Popocatépetl, next to Mexico City, 30 million people in Mexico City, and there's a big volcano right next to it. Whew, it makes for a lot of very fertile land. This is good in a way if you live next to a volcano, as long as the volcano does not erupt. So, what do we do? What can we do? Usually it requires very careful monitoring, and it means long-term monitoring. It's not good enough to just check on your volcano every now and then on a Sunday afternoon. You really need to look at your volcano every day. You need to have 24/7 monitoring, surveillance out there. So, and what we usually have to do is we have to establish a baseline. What does the volcano do when it's calm? Because only then can we recognize if something is changing. So that requires us to really spend time and logically also resources at our volcanoes. So less favored region, financially less prosperous region, can often not afford such long-term surveillance, and that is partly the reason why we have a higher death toll in countries that have lower income on average. So one of the first volcano observatories is actually this one here, the Osservatorio Vesuviano, and you see Vesuvius volcano in the background. Then we had the 1920s, seeing, for example, the Palayan Volcano Observatory, the Hawaiian Volcano Observatory, and then in the 1930s, the early Indonesian observatories were built up at the time, mainly from the Dutch colonial administration, and then later they were, of course, taken over by the Indonesians, and this is providing us with long-term monitoring. The 1871 Vesuviano Observatorium, this was merely a chap with, some binoculars looking at the volcano every day, every hour, making a note. And then, of course, increasingly, there was photographic evidence and things like that. And now we're more and more technical about how we monitor volcanoes. So this is an image from Indonesia from the 1930s, where photographs were taken, and there certain phenomena were recorded. And there was actually a very good record that now allows us to go back and say, oh, there's a certain rhythm to certain volcanoes. Even the information is, of course, not as good as we would do it today, but we still can learn a lot even from fragmental records at the time. So I happened to visit the old Vesuvius Observatory, which is now a museum. There's a newer one closer by, and the Italians gave me that wonderful little field vehicle in the lower left. I thought it was a terrible kind of thing, but yeah, I never had another Fiat in my life. So, here, this is what we do at volcanoes. So here, we're monitoring active volcanoes with many different methods today. We're checking at the seismicity. Does the ground shake? We're checking does the tilt. Does the ground actually deform? Does it bulge up? We look at it with cameras. We look at the temperature. We see whether the water in the area is suddenly having more sulfur or having a higher temperature. We're checking this. The thermometer in the top right here, it's in a fumarole at an Indonesian volcano. You may just about be able to see it. It says it's over 200 degrees hot. And it's maybe a little too small, but in the top right of that image, there's actually a little bit of liquid sulfur, and liquid sulfur usually requires some 250 degrees centigrade. So this is kind of giving us indication, and if that changes, we will make a note of that. So nowadays we also increasingly use remote sensing. We don't always have to go there, and there we can, for example, check ground deformation with satellites, and there's an image, a radar interferometry image in the bottom right that gives you these fringes when the ground is moving, and this shows, oh, something is bulging up, for example. So usually we check different parameters. We check expansion, we check seismicity, we check gas, temperature and chemistry, but also heat flow in, for example, aquifers in the region. And Usually, we expect all of these parameters to change if the volcano is waking up. So we have different specialists looking at these, and if several of them say, oh, we have an issue, something is changing, then you need to get alert. And then you need to think about, how long will it take? How dangerous is the situation? How many people will be affected, etc., etc. So, volcano monitoring, therefore, looks at a whole range of things, a multi-parameter approach, and we're looking at all of these different things that I'm listing here. I mentioned most of them, and this is what observatories do. They observe these changes, if there is any. So, this is what I mentioned, radar interferometry. These days, we're looking at things remotely as well as on the ground. We have boots on the ground as well as all sorts of remote sensing. And remote sensing is, for example, also a temperature method these days. We can, with satellites, actually see any thermal changes. This is Merapi in Indonesia. And you see when it was waking up, in the crater area, you see the colored pixels. And that tells us, oh, there's heat coming out now. So you don't actually have to go into the crater anymore. You can actually see that there is a change remotely. Then we can also work out how ash clouds travel. This is Etna, and this is from the ESA, the European Space Agency. And there you see not just the cracks in the lavas, and you also see the direction with which the ash is traveling, and this allows you to make a calculation which areas will be affected downwind from ashfall, from, well, low air quality, etc., etc. So, and this goes further. This was one of the earliest scenarios where this has been applied. This was an eruption in Alaska, Mount Spur, and there we see the colored ash and gas cloud coming from the spur, and here you see the travel speed, and if you know the weather and the wind direction, you can actually see how the material is traveling, in this case all around the northern part of the US and Canada. So this then allows people to be warned in time about low air quality, gas in the air, and things like that. So after the Mount St. Helens eruption in 1980, which was a bit of a shock for everybody, the USGS really put a lot of effort in, and there was another eruption 2 years later. And nobody really knows about this eruption because it was completely non-spectacular, because the USGS did their homework and they were able to predict the eruption within 2 hours of its event. And here they have mapped the seismic energy, the dome expansion, the tilting of the flanks, and the SO2 emission. And all of these parameters were pointing towards the same thing, allowing them to say, there will be an eruption tomorrow at 12 o'clock, and then it was at 1 or so. So, and this is of course the same for the Canary volcanoes. This is an image in the right-hand side of the volcano on La Palma. And this was in the exclusion zone. People were not allowed there. Only volcanologists could go that close. And in the bottom left, I'm showing the seismic activity. The eruption is the stippled line, and there was quite some evidence for the volcano waking up actually in the weeks before the eruption. But scientists knew already 3 years before that something was in the bush there. The local population, of course, didn't really realize this, but the scientists knew an eruption was going to happen sooner or later on La Palma. So, this is now satellite imagery from La Palma as well, and this is just in the days up to, leading up to the eruption. And here you see these fringes again, radar interferometry. You see these fringes showing that the ground was swelling up, and just where they all culminate, there we had the eruption center. So these methods even allow us to say partly where the volcano might actually erupt, where the vents will be. So this hopefully puts you at ease. All the Canarian volcanoes are monitored. So we will find out if there's an eruption. And the good news is we're going to Fuerteventura tonight. Fuerteventura did not have a volcanic eruption in at least 130,000 years. So we're all good, I think, and can enjoy the rest of our trip. And I thank you for your attention.